Imagine the following situation. Imagine our familiar characters Alice and Bob. Imagine that Alice has two classical bits, X and Y, that she would like to send to Bob. Unfortunately, she can only use a quantum channel, and moreover, there's a restriction. She's only allowed to send one qubit, just a single qubit. At first sight, this looks impossible, because last week we discussed Holevo's bound, and we discussed the transmission of classical information via quantum systems through a quantum channel, and we learned that a quantum bit, a qubit, can carry at most one classical bit. So this seems a task which is impossible, which is violated by our discussion of Holevo's bound. There exists a protocol that allows Alice to do that nevertheless, but of course it has to involve a trick. It has to involve some trick to get around the limitation that we discussed last week. And the trick consists in using a bell pair that Alice and Bob have shared in the past. Yeah, so it's you can argue whether this is sort of a fair protocol, because effectively there's one more qubit involved, namely the second member of the bell pair. However, the bell pair could have been generated and shared a long time ago. So, I don't know, a week ago, Alice and Bob may have produced this bell pair and put it in storage. And each of them is in possession of one of the members of the bell pair. So they did that, Alice and Bob did it at some point, and then the necessity arises for Alice to send to Bob two classical bits. And she's only allowed physically to send one qubit. And she can do it with this protocol that we're going to discuss if the two use the previously produced bell pair. Let me guide you through the protocol step by step. So the starting point are these two classical bits, designated with double lines, and the bell pair in one particular bell state, beta 00, and one of the members is in the possession of Alice, and the other member is already in the possession of Bob. So they did the sharing in the past. Let me remind you what this bell state beta 00, what this looks like. The bell state beta 00, that's precisely the state in which we will start the protocol. So that's the psi 0. That was the superposition of 00 and 11 over square root of 2. This is our starting point. Now, what does Alice do next? Alice uses the second of her classical bits, so this Y, to control a Pauli X. And after this first controlled operation, we have a state psi 1. Of course, affects only Alice's qubit. Yeah? So here in the, when you look at the state of the Bell pair, the first label refers to the member which is in possession of Alice, and the second one refers to the member in the possession of Bob. So this controlled Pauli X affects only Alice's member of the Bell pair. And it's a flip in the standard basis. Yeah, so if the classical bit is 0, then nothing happens, and 0, 0 remains 0, 0, and likewise 1, 1 remains 1, 1. If the classical bit is equal to 1, then Pauli X is executed and Alice's qubit state is flipped. We can summarize by writing y0 plus, and then 1 plus y mod 2, 1. So you see, if y is 0, then nothing happens, and if y is equal to 1, then the Alice's qubit basis state is flipped. Next, Alice uses the first qubit, x, to control a Pauli Z operation. What does the Pauli Z do? When you apply Pauli Z to a basis state, if you apply it to the basis state 0, then nothing happens. If you apply it to basis state 1, then you get a factor -1. So let's see how that affects the state of our qubit pair, state psi 2. Let me take out the factor 1 over square root of 2 and focus on the rest. Let me consider two cases. Either x is 0 or x is equal to 1. If x is 0, then of course nothing happens, and the state is still y0 plus 1 plus y1. If x is equal to 1, then, as I said, if x is equal to 1, then Pauli Z is performed on the qubit. And then let's see what happens to this state here. So the basis state y acquires a prefactor -1 depending on whether y is equal to 0 or 1. And here the 1 plus y also acquires a factor -1 if 1 plus y is equal to 1. So there's several possibilities here. However, what is certain, regardless of the value of y, the prefactor in front of 1 plus y will be minus the prefactor in front of the y. So there will be a relative minus sign. There might be an overall sign, which we don't care about because overall phase factors and overall signs are physically irrelevant. So let me indicate this here in front of the 1 over square root of 2. There might be an overall sign, but we don't care about that. But what is clear is that whatever the value of y, the action of Pauli Z will introduce a relative minus sign. So we will have y0 minus 1 plus y1. Then Alice is done. And so this is the part of Alice. Alice is done with her part and with her operations, and sends her member of the bell pair physically to Bob. So this is the 1 qubit that she's allowed to transmit physically through the channel. Yeah. And this qubit arrives now on Bob's side. What does Bob do? Bob still has his member of the bell pair, and this is the second line down here. This indicates Bob's member of the bell pair, which was always in the possession of Bob, and now in addition he receives the other member from Alice. And the first action that Bob performs is a controlled knot on these 2 qubits. And let's see what the state of the 2 qubits looks like after this controlled knot. After this controlled knot, we have the state psi 3. And let me ignore overall signs, and let me ignore the 1 over square root of 2 and just write the proportionality here. That's all that matters. And let's keep the distinction, the 2 cases, x equal to 0 and x is equal to 1. So what effect does the controlled knot have? Let's consider first this basis state here, y0. If y is equal to 0, then y is the control qubit. And if the control qubit is in the basis state 0, then nothing happens. So 0, 0 remains 0, 0. If y is equal to 1, then the target qubit flips. So 1, 0 becomes 1, 1. And we can summarize this succinctly by writing yy. So y0 becomes yy. Now the next step, in the next step, 1 plus y, that's the basis state of the control qubit. 1 is the target qubit. And remember when we discussed early on the C0 gate, one way of writing the action of the C0 gate was to say, on basis states, was to say, well, the control state of the control qubit always stays the same, the basis state, and the target basis state, t, becomes t plus c mod 2. So we can say this 1 becomes 1 plus y mod 2. Yeah, but 1 plus 1 mod 2 is 0. So this becomes effectively y. Okay. So in both cases here, in both contributions to the sum, the state of the target qubit becomes y. And the same holds also for the case x equal to 1, only that we still have the relative minus sign. So there we have yy minus 1 plus y. And then there's one final step, Bob applies to the first qubit a Hadamard gate. And the second qubit remains unchanged. And then let's finally see what happens after the Hadamard gate. Well, if you look again at the state psi3, the second qubit is in the basis state Y, and this will not change because the Hadamard applies only to the first qubit. Now, the first qubit is in this case here is in a superposition state Y plus 1 plus Y, so the flipped basis state. So depending on the value of Y, it's either 0 plus 1 or 1 plus 0, doesn't really matter. So the first qubit is in the plus state. That's what we defined as the plus state. And when you apply the Hadamard gate to a plus state, then this becomes the basis state 0. So actually psi4 is in this first case where x was equal to 0. The psi4 is 0y. In the second case, where x is equal to 1, in the second case, if you look at psi3 again, also the second qubit is in the basis state Y, and the first qubit is in a superposition Y minus 1 plus Y. So a standard basis state minus the flipped standard basis state. So it's either 0 minus 1 or 1 minus 0. That's up to an overall sign. That's what we call the minus state. And when you apply a Hadamard gate to a minus state, then this returns the basis state 1. So in that case, psi4 is the state 1y. So that's for x equal to 1. Or you can simply summarize that. You can summarize these two cases. This is simply up to an overall sign, the state xy, the basis state xy. And now it is clear that if Bob performs on the two qubits measurements in the standard basis, so the state psi4, that is the basis state xy, if Bob now performs measurements in the standard basis, then for the first qubit this will return x, and for the second qubit this will return y. And we are done. Bob has now, after his measurements, he has obtained the two classical bits, x and y. And all that was transmitted physically in the course of this protocol was just a single qubit, namely Alice's member of the Bell pair. Let me run through this algorithm again on the slide, step by step, and quickly summarize what we calculated on the sheet of paper. So we started out with psi0, and then Alice used the second classical bit to control a Pauli X, then used the first classical bit to control a Pauli Z, then physically sent to Bob one qubit, namely her member of the previously shared Bell pair. Bob receives that qubit from Alice, puts it together with his own member of the bell pair, and performs on the 2 a controlled NOT. Then on the first qubit a Hadamard gate. And then Psi4 we found was a basis state, XY. So when Bob then measures in the standard basis, he recovers the classical bits X and Y. And that's the magic trick. So that's sending 2 classical bits with 1 qubit, using the trick of a previously shared bell pair.